Okay, hi everyone. Welcome to another webinar hosted by Seek Thermal and Andy Starnes of Insight Fire Training. We have Andy here who brings over 30 years of experience from his career as a battalion chief in Charlotte, North Carolina. So Andy, thanks for being here with us today to talk with everyone about commonly encountered problems while using a thermal camera on the fire ground and how to resolve them. If you guys have any questions, please just type them in the chat and we'll do our best to answer them in a timely manner throughout this webinar. And with that being said, Andy, take it away.
Thank you, Jordan. So the title of this webinar is Overcoming Limitations in Thermal Imaging Usage. My hope is that this webinar helps clarify and clear up a lot of misnomers and things that occur to firefighters that they may or may not understand, and possibly how to correct some of those. As some of you may know, my name's Andy Starnes. I've been in the fire service 34 years now. I retired as a battalion chief 2 years ago. I've been involved in thermal imaging now going over 16 years. I've assisted in thermal imaging product development with Seek Thermal and numerous other manufacturers. Our company is a group of thermography certified veteran fire service members from around the world. We train internationally, and we developed the very first collegiate-based thermal imaging certification in partnership with Western Kentucky University, and along with Kentucky Thermal Institute, and Seek Thermal had a hand in sponsoring that as well. So we are very fortunate, and I'm very blessed to have a family that we live here currently in Shelby, North Carolina. My wife of 20 years and our daughter Emma, who is about to turn 16 this year. Interesting times in our lives. Our goal is to help firefighters work in the darkness, and we help them out of the dark of the fire and help them out of the darkness of some of the struggles they may have in their lives in behavioral health. We support numerous nonprofits. This is one of them, called 5 Alarm Task Force. So if you'd like to learn more about that, reach out to me directly. But today we're going to talk about some things that can help you overcoming limitations plus defining those limitations. But the first thing I need to ask you is you need to know your brand of camera and model. For example, these are 4 different decision-making models from Seek, along with some resources with them. When we ask firefighters, when we begin the class, every time we train, we ask them what their name is, what brand or model of camera they use, and what's one thing they'd like to learn. Some responses I get are usually a red one, a blue one, or I don't know. Any other tool that a firefighter has on their truck, whether it's their SCBA, whether it's their gear, they know. But a thermal imaging camera is not prioritized in its use, in its training, or even what brand or type they're even using. And this is a big issue globally, not just in the American fire service. So first, learn your model, brand, when it was made, what features it has, and then we can talk about limitations. But we have to start with knowing your brand and model of camera. If you're using a Seek Attack Pro decision-making camera, the way to differentiate these pretty quickly is to look at the top of the camera. They have 4 different colored stickers. The black is the Attack Pro, your basic model, has on-off flashlight and spot temperature. Attack Pro S, the kind of bluish tint sticker there, has survey mode added to that. The VRS, the kind of orangish red color one there, has video, record, survey, and a slightly higher dynamic range. Whereas your yellow sticker, any sticker that you see like this that has that SEI designation on it, implies an NFPA 1801 certification. That typically costs more due to the amount of work that the manufacturer has to go through to get it certified. But this is the easy way for you as a firefighter to differentiate the tops of these. The reason I say that is I have numerous people email me and say, hey, we can't get our camera to go into survey mode. And I say, well, what kind do you have? Well, we have the Attack Pro. I said, which kind? Don't know. They send me a picture of the top. They have the Attack Pro Basic. Attack Pro Basic does not come with survey mode standard. You have to upgrade that. So firefighters don't know what they don't know. We need to upgrade our knowledge along with the technology. So what's the biggest limitation in TIC use? Surprise, surprise, us. Out of 20,000 students on our average year, when we ask everyone in the room how much training they've had, less than 1% will raise their hands and have more than 1 to 2 hours other than given to them by a salesperson. And almost none of them have had live fire training with the device. So why do you think we have consistent problems with this device? How many hours of SCBA training does a firefighter have to do to wear that SCBA after they finally graduate recruit school? How many hours do they spend donning and doffing, putting on and taking off their PPE, learning how to throw ladders, pulling hose lines, working with nozzles, forcing doors? extrication, everything they do, multiple sets and reps, learning how to do it, learning the intricacies of each device, contraindications, all that. There are more hours, clinical hours of firefighters required in the EMS side than there are on the hands-on fire side. And then when you break it down to all the way down to thermal imaging, there's very little done, even though there is training should be required per NFPA. So how can we overcome limitations? First, we have to define the fact that we are insane. For the last 30 years, since these devices have been in place, it has been a cycle of insanity with no focus on training. Then we have some training, then it goes away due to budget constraints and lack of prioritization. So we have no focus in training on education, which leads to no positive results. So what we see on the display is definitely not what we get, which we'll discuss that. And then we have improper use, which equals improper results or disaster. And then false information without verification, which we'll talk about. This is not a thermometer. This is a snapshot from a NIOSH report where the use of the spot temperature was listed as one of the contributing factors to 4 firefighters dying that day and 1 dying a year later. Engine 51 to command, we have a 184-degree reading on the door, thermal imaging reading. Firefighters who are being instructed to call out temperature measurements have no idea that that number they're calling out is not exact, and they don't know what it represents. In most cases, it's a small piece of a bigger picture. And we're going to talk about why that's dangerous and what we should be reading versus trying to call out exact measurements. Before we go further, you need to understand that fire service TICs do not see gas temperatures. They're not hazmat cameras. We'll talk about optical gas imaging, how that's different. They don't even read smoke temperatures correctly. Smoke temperatures can affect it and change it, and they definitely don't read shiny surfaces accurately. Fire service TICs provide something known as an apparent temperature, which is a gross estimate, hundreds of degrees in variance depending on several variables. And one of the biggest issues we consistently see is firefighters say, I didn't see any color on the camera. I don't know why I got hot. The absence of color is not the absence of heat. You need to know your camera. Many cameras do not show colorization until far, far too late. And some, in most cases, when you're remote from the fire, the surfaces have not heated up. You'll just see grayscale convection currents. The same type of convection currents that cooks your pork tenderloin in your air fryer twice as fast. NFPA 1971 defines one of the tests they use to basically cause your gear to fail, called a forced air oven test. There's no color when that is viewed through a TIC, but there is heat. And we're going to talk about why we need to read heat, not temperature. I want you to look at this video of these firefighters moving from the first floor to the second floor in this Draeger container. And I want you to ask yourself, is this a problem? They're walking up a chimney. Gear is so good, it's protecting them for a short amount of time, but using a camera in here is not the problem. Understanding the science of fire behavior and flow path, and what you're not seeing is this is a massive amount of heat moving up these stairs. This is not a good place to hang out and play. And we've done this in our own company, so I can't judge anybody for it because we were involved partially in this. So we have to understand that if you see fast moving grayscale convection currents like this is a defined flow path. This is heating, cooking, and killing anything in its path. Even though you don't see color at the upper end and you see color at the bottom, trust me, the top is extremely hot. So understanding what you're seeing is critical. You have to have a knowledge of how to interpret thermal data first. What it means, what does it not mean, and understand the limitations of the device. Fire service TICs can see a lot of things. First of all, 75% of energy transfer in a fire fall into the range that your camera can see. Your eye only sees less than 1% of all visible light. So when you see that, that should make you understand how much we're missing, that this camera is seeing between 7 and 14 microns, well, over 7 times what the human eye sees, but we don't see everything. We understand that heat can be detected behind certain surfaces, but not all surfaces. The thicker something is, the better it's insulated. The type of surface all can hide heat signatures from firefighters. Reflective surfaces, numerous variables that come into play. And then we have to understand a concept called thermal bridging. We talked about this in our size up webinar. Basically, thermal bridge is a bridge between the interior and the exterior, an area of weakness within inside of the structure that allows heat to transfer, otherwise known as a heat bridge, from one point to another that it should not be there per the engineer or person who built it. But it allows heat to escape and then heat up an area on the surface, which the camera can detect in a non-uniform pattern. It's a lot of words to tell you. It's going to show you a hot spot on the outside of the building, depending on the surface and how thick the wall is. How's that? High moisture environments can also be extremely counterproductive or contraindicated to the tick itself. And then another one is fire service ticks do not white out due to heat. We haven't had a whiteout due to heat problem in over 25 years. When cameras went to dual gain and started adding colorization to them and changed from BST technology and pyroviticon into amorphous silicon and the type of detector, they added colorization and you had dual gain, which allowed the camera to see more heat, and it didn't saturate. Cameras can saturate now, but you're going to see a massive amount of colorization when that occurs. We're going to discuss the whiteout effect and why that's not due to heat necessarily and how you can fix that. And here's a big one for all my search friends. Yes, you're hearing this from a tick instructor. Fire service ticks do not detect victims very easily, especially in certain environments. They may blend in, they may disappear, and depending on how you're using them, you may not see them at all. And depending on whether they're alive, dead, buried under something, they're not always visible with a thermal imaging camera. That doesn't mean you shouldn't look, but it will tell you it's a lot harder than most people realize. This picture on the left is two cameras looking at the exact same window, showing the exact same picture. This is the definition of a thermal bridge. This is a fancy word for conduction, heat transfer from the inside of this window to the outside. And you're like, I thought ticks can't see through glass. Well, they technically don't see through anything. We're going to show you what that is and why that is. Because limitations are not necessarily a limitation as much as it is a failure of our ability to understand what the device was originally intended for and how it's being used now. First of all, the number one misuse of this device is firefighters calling out numbers or using it to get exact measurements, trending temperature measurements, using it in EVs or for looking at exact measurements, thinking they're able to detect thermal runaway by a spot temperature. This is a spot temperature example. It says it's 97 degrees. Do you trust that? That is exactly why this could be dangerous. This is also why it was listed as a contributing factor in 3 separate line of duty deaths in the NFPA 2021 standard on 1801. So we have to know more about what we're looking at than what we're looking through, and then know what our camera actually detects and how that little reticle, that little square in the middle, how it's calibrated. What is it designed to do? And why newer cameras don't even have a spot temperature when you turn it on. Fire service ticks do not detect gases. A lot of people claim they do because they see movements that look like gases. We're going to explain what that is. Fire service ticks should not be used for temperature measurement on lithium ion incidents. You can look for heat transfer, non-uniform patterns, colorization, lots of other things. But if you're looking for measurements, you're going to be in trouble. I'm going to tell you why. Because if you stand at the wrong angle, the wrong distance, have atmospheric attenuation between you and the target, such as wind and rain, good luck. You could be about like one of these incidents we're going to discuss. Fire service ticks do not see through things. They're not X-ray vision, ladies and gentlemen. I don't think TV or Hollywood helps us with that. And please, they do not see through water. Do not stand and look down at the water thinking you're going to see a victim at the bottom of the lake. The water is a solid surface to the device. Here's your window of opportunity. Would it surprise you to know that there is such a thing as window thermographers? People who take a very specific type of camera and go and look at commercial buildings, even residential structures, and scan windows looking for signs of inert gas or argon gas failure to tell whether or not the window is insulating that building anymore or it's failing. So if they can do that, what can you do? So yes, we can't see through glass, but this is an example of single pane glass, which is why we don't use single pane glass in newer homes predominantly, because they are not energy efficient. They allow energy to go through. When you start adding things like single pane, efficient vinyl frame windows, or hurricane glass, or my friends overseas that have Lexan on the outside and they're high security glass, triple pane windows, much, much more difficult for your camera to detect something through the window transfer as much as you would detect around the edges, such as in this picture. This is a 2x6 studded wall done by Project Kill the Flashover back in 2014. They built these walls and inserted them into the end of the container with different types of walls, with different types of ventilation points, doors, windows, etc., with a full flashover load of fuel, such as a couch, chair, pallet, and straw. The fires were ignited, and then they would look at the exterior of the structure through the actual wall here and around the window to see what they would detect. In this older ISG X380 camera, you're detecting the cameras in medium sensitivity, which most cameras that would be low sensitivity, indicated by the green triangle in the upper left-hand corner, which means the camera is detecting significant heat, number one. Number two, we're seeing what's called a non-uniform heat signature around the top half of the window, which is a thermal bridge. It's in a wispy pattern as heat is transferring where the caulk is burned away. And then number three, if you look closely, you can see these weird random patterns on the glass that are not reflections. They're the glass heating up. Quick tip, if you look at a double pane window while doing a size up, and you see the window looks like there's wind moving on the other side of that glass, the double pane glass in that particular example, most likely the inside pane has failed, and you're seeing heat movement on that next pane, which is soon to fail thereafter. So watch for these types of things when you're doing size up on windows. It's not an always or never. It is contextual, it's environmental, and it's up to the end user knowing what they are holding has limitations, but the biggest limitation is our lack of education. And this one is probably the biggest. Why did NFPA 1801 remove the spot temperature? We get actual complaints from firefighters. It doesn't have the thermometer on anymore. That's wrong. We want that back. Ladies and gentlemen, I'd encourage you to do some homework. In 2021, NFPA 1801 removed the spot temperature feature due to the fact that it was listed as a contributing factor in 3 separate line of duty death incidents. The actual committees on this actually tried to get this removed earlier. So this is not something new they fought against. They tried to get it out. But these inaccuracies in the spot temperature are due to variables such as emissivity, which is the surface itself. Is it a shinier surface? Is it a rougher surface? Atmospheric conditions such as wind, rain, relative humidity, surface properties, like what we just discussed. And standing at the wrong angle, distance, all can change it. They took this away to try to prevent or reduce the risk of injuries, burns, and yes, my personal favorite, rekindles. You know how many reports have been sent to me that were rekindle incidents, and the initial closing out of the report stated, the fire was extinguished, engine XYZ cleared the room, the thermal imaging camera showed a 74-degree reading, and the fire extinguisher left the building. 3 hours later, they come back, the place is rocking. You just read a 12-inch circle or square, depending on the type of camera, what it's measuring. And did you point it exactly at the right spot? Did you hold it perfectly still? Did you feel the reticle? Did you account for all those variables? No, because the camera doesn't allow you to. It's non-adjustable. And it even says in the NFPA document, despite all thermal imaging manufacturer warnings not to use the temperature measurement to make tactical decisions, it became apparent in 3 recent NIOSH firefighter fatality reports, there's a lack of understanding on behalf of these features. No kidding. Do you know, I get at least 1 email or phone call a week. Hey, we had our 2 cameras out. We were looking at surfaces. One said it was 86 degrees. One said it's 72 degrees. We need to have them calibrated. No, doesn't work that way. They calibrate them for focus, for issues within the detector, but straight out of the box, I need you to hear this. Some of these cameras are plus or minus 5 degrees off. Some are off 7.2 degrees. Some are off 41 degrees, straight out of the box before you do anything. And that makes a huge, huge difference. Read our most popular article called The Danger of the Spot Temperature, where we discuss this. This presentation will be available at the end for anyone who's interested in it as well. So we know they're not thermometers, then why are we calling out temperatures when we do our size up or moving down a hallway, which is enlisted in firefighter SOGs across the US and in certain countries? Because they haven't been educated on its danger. And also, if you use it during overhaul, if you're not careful, it can be misleading. You got to understand that that spot temperature was calibrated where all the variables are controlled. It was held perfectly still, perpendicular to target in an air-conditioned warehouse at a preset temperature, preset emissivity, no wind, no rain, no reflective surfaces, and you don't get to control the variables in a house fire. Even using an overhaul, if you hold it incorrectly, stand at the wrong angle, look at it differently from the last time you looked at it, trending measurements are not only misleading, but they're not going to work. because there's no way a firefighter can stand in the exact same place every time and hold the camera in the exact same position and have the exact same environmental factors every time they look at that spot. If you'd have to consistently point at the same spot, perpendicular, and control the wind, the rain, the emissivity of the surface. It cannot vary. Yes, you may see some measurements that vary up or down, but the target has to be the same and the variables have to be the same. This works in a lab, ladies and gentlemen, but does not work well in an IDLH environment. Fire service needs to understand these are not meant to give exact measurements. One simple little research about how hot a candle flame is, or how hot an incandescent bulb is, or how hot a halogen bulb is would shock you to know that they go anywhere from 1800 to 3600 degrees Fahrenheit, but yet my camera only says 1200 degrees. I believe the fire is greatly, greatly hotter and more dangerous than that. And we know that factually. So why is it not accurate? Let's go through the variables so that we can break this down for anyone who wants the actual information. Number one, the material being measured. What is it? What is it? Shiny, rough, its ability to absorb or reflect heat. The definition of emissivity is the ability of an object to emit, absorb, or reflect heat numerically between 0 and 1. 0 is a perfect mirror or reflective surface. 1 is a perfect black body or something that emits or absorbs heat well. How hot is the object? The hotter it gets, the more it could change in its variance and how the camera interprets it. Where are you standing? The distance. When you take a thermography class, they talk about the acronym FORD, focus, range, and distance. Those have to be correct. If I'm not in the right distance, the camera's not going to measure it correctly. Do you know what your camera was calibrated and what distance it was? The angle of incidence is equal to the angle of inclination. If I stand at a 45-degree angle to an object, the energy that's hitting that from the opposite 45 degrees is coming at it. I'm not reading it directly. I need to stand perpendicular to the target every time, which is really interesting if you take ARF training, because they tell you not to stand perpendicular to a landing gear, but they want you to come up and measure it and give the pilot a reading, an actual temperature reading. Hopefully they're using a laser thermometer, but you shouldn't stand straight in line with it, 90 degrees to it, because it's dangerous. Have you looked at the brakes on a Boeing or an Airbus? They're quite shiny. I don't think I'd want to use a standard infrared camera. The cleanliness of the lens is a big deal. If we're not wiping the lens periodically, we're not going to see. The object does not fully fill that center target area known as the reticle or the crosshairs. That can cause a false reading. And not all objects emit radiation. I know this isn't the nerd to know category, but please bear with me. There's hemispherical emitters, there's Lambertian emitters, or perfect black bodies. They emit energy differently based on their surfaces and their shape. If I have a curved surface, that changes it. If I have a perfect black body, such as you're looking at something like 0.95, closer to 1 emissivity, they're going to give off energy better than something like a stainless steel stove or diamond plating on a fire truck or a polished stainless steel pot. That's called low emissivity. Those who are homeowners, you know this because your windows are low E glass. Scientists do everything backwards. Don't ask me why, but if they say down, they mean up. Low means high. Low emissivity means high reflectivity. And this can all be found, ladies and gentlemen, in NFPA 1801, the 2021 edition, which has now been consolidated under NFPA 1930. I know that was a brain dump, but this needs to be shared. People are using these devices incorrectly, and they're getting hurt and killed. And this is not good. You try to use this in the wrong environment, you're going to end up with a disastrous result. If you do things like this and call out a temperature measurement for not realizing where you're pointing it, both of these temperature measurements here are pointed at the corner of the colder area of the wall, 119 degrees Fahrenheit, 112 degrees Fahrenheit. I apologize to my European friends who know that Celsius is better. One day we will change, but right now we're in Fahrenheit, okay? The picture on the left's TI basic, the picture on the right survey mode. Obviously the colorization is greater in survey mode because it colorizes 150 degrees Fahrenheit. Point being, we don't read the spot temperature, we read the heat. You look for convection, you look for colorization, you look for thermal layers, you look for everything. You don't look for single point measurements. If you do, you're going to be in trouble, okay? This is where we get in trouble. This is where firefighters get hurt or killed. Read the big picture, not the small temperature measurement in the bottom right-hand corner. I've went as far to buy little happy smiley face stickers and stick them over that number when we're doing training to keep students from calling out that number. This is a Bullard video showing you why you should not use a trending or call out temperature measurements. Watch the bottom right hand number if you can and tell me how much it changes. We started at 52 degrees, we're at 509, we're back to 90, we're at 211, we're at 106, we're in low sensitivity, by the way. We're in 101, 106, 141, 332. Is that confusing you? That's like somebody is basically their foot can't stay on the gas consistently and they're just going back and forth and back and forth. That's because we're constantly moving this around, which the smarter move would be to say, yeah, it's in low sensitivity. Yeah, I have convection currents coming from the left-hand side, and I have colorization. And in this camera, yellow is 500 to 800 degrees, not 62. Yes, it may have a cool area in the floor, but up top is definitely not cool. Understanding when your camera switches to low sensitivity, in this case, is a big deal. And look at this. Every time I reread this, it sticks with me. Surprise, Arizona, hazmat team made entry to an energy storage system. This is numerous hours after the incident started. Shortly after opening the door, the engine captain called a max temperature of 104 degrees Fahrenheit with no active fire or visible arcing. Where did he get that number from, ladies and gentlemen? This was 3 minutes before they called it deflagration. I would call that an explosion if they stated in the document, which they state right here, that he and the firefighter were ballistically propelled against and under a chain link fence that surrounded this unit, and they came to rest 73 feet from the open door beneath a bush that ignited in the event, where the other firefighter came to rest 30 feet from the open door. The other firefighters were projected towards a transformer and remained within the fenced area. The entire team lost consciousness, and this event dislodged or removed their SCBA face pieces and helmets. What were we reading? A spot temperature of a surface of an extremely insulated object that's designed to prevent heat transfer because lithium-ion batteries don't want moisture or air to get to them. Multiple layers of protection, multiple layers of insulation. Reading a single point measurement is a bad idea. This is not the proper use of it. It's not their fault because from my understanding, there's not a lot of training in that area either. You can read about it. UL did an entire report on it. And as I said earlier, the absence of color is not the absence of heat. Watch this video, GoPro and Attack Pro, and tell me if you can't see the bad things coming. Fast moving smoke, fast moving convection currents. Dodson taught us to look for volume, velocity, density, and color. Yeah. Yeah, Rob Backer's doing a great job passing that legacy along. So you put both of those together, ladies and gentlemen, and you can see this coming, as Dr. Gassaway says, see the bad things coming. It can go from black, gray, white to a very deadly event quite quickly. This is just a flash overload in a Connex box. This is not furniture. This is not mattresses. Big difference. Fast moving grayscale convection currents are heat. Here's the challenge though. Sometimes they're hard to see. Remember these statements that will help you when you go into a fire. Convection can indicate severity and direction of the fire. The height of the convection currents can tell you where is the fire. Is it coming from a base and moving up from high pressure to low pressure, moving towards the upstairs? Is it all the way to the floor, showing it's in a full unidirectional flow path or exhaust? Colorization can provide information about superheated surfaces, location of fire, but a lot of color can hide information. Convection currents can be hard to see. The thermal layer height will be high or farther up higher away from the fire, and as you move towards the fire, it will descend, pointing towards the seat of the fire. First video, Fire Pro 300, looking at a fire downstairs with convection currents moving upstairs. Very hard to see convection in this particular incident. Very small amounts of heat, not a very aggressive fire. We changed to survey mode. Tendency here would be to be locked in on color, and like my friends in Loudoun County, they had a close call years ago where they went above the fire. If you weren't looking closely, you could tell the fire is to your right. That's why when we talk about doing scans, you need to do 180 degrees. And our 4 points of scanning techniques that our cadre teaches, instructor Thomas Anderson does a great job of explaining that. You need to see the big pictures. Slow scans, quick work. And then if you watch this video on the right here from Wilson, North Carolina, when we were fortunate enough to train, or actually this is not Wilson, this is Gilbert, I'm sorry, Gilbert, Arizona. We'll give them both a plug. You can see the convection moving across and back towards the firefighters. Convection can tell us direction and severity. This is an awesome burn building, by the way. When you see those type of tiles, you should get excited because that's, if I remember correctly, they can take up to 3,800 degrees. Beautiful convection, beautiful colorization, pointing you right towards the fire. And as my friend Kyle Romagus says, if I throw some water down range, give it an aggressive hit and stop, I can force a rebound and make the fire tell me where it is, because it's going to come back and it's going to tell me where it is. And then I'm going to flow and move right to the seat and it's game over. Use these concepts instead of spot temperature measurements to help you win on the fire green. Okay. Now let's cover the other contraindication. Well, I see movement stuff like that video. That's gases. You can't lie to me. I have a FLIR. That's the forward-looking eyeballs. I can tell you that's movement. Okay. Well, let's talk about it sensibly and like human beings here. Your fire service camera detects long wave infrared radiation between which one you read, says 7 to 14 or 8 to 14 microns. A micron is a millionth of a meter. It's a narrow band of light that the eye cannot see. It was discovered by Sir William Herschel in 1800, and he called it dark heat. The area outside of visible light was the hottest. That's what he called it first. Okay. Most gases, such as carbon monoxide, methane, propane, are invisible in this band because they don't strongly absorb or emit those wavelengths. Whereas if we use something called an optical gas imaging camera, which starts at $40,000 and goes up to whatever you want to spend, by the way, uses narrow filters to detect those absorption bands of specific gases such as methane. Notice methane's in the 3.3 micron range. However, you cannot always see gases with a thermal imaging camera, but you can, in certain cases, see the effects of them. This is a 2-inch gas line cut 3 feet underground. The little dark spot sticking up is a red or orange pipe from the cable company. They were running their fiber optics lines through Charlotte, North Carolina, and they hit a 2-inch gas line. We were walking back to the command post. We noticed a very dark V pattern on the ground. It was 100 degrees that day. Why is the ground significantly cooler and darker? Because that gas was pumped from the factory around 50 to 60 degrees Fahrenheit, underground, insulated, and then that cool gas hit that hot dirt and produced a contrast. Thermal contrast is what your camera's picking up. So let's talk about what the difference between an optical gas imaging camera versus a fire service TIC. OGI cameras pick up all kind of different gases, but they are filtered to pick up a specific wavelength. Look at the difference between methane, carbon dioxide, carbon monoxide, and other gases. Each one of these cameras is filtered for that. You have to buy, in certain cases, one camera for one type of gas. There are certain cameras that pick up several types, but in many cases, you could buy just one camera to pick up a specific type of gas. And then some of them use called a tracer gas to pick up gases that don't fall in the ranges so they can find those and find the leak. So anywhere between 3.2 to 3.2 to 5 micron, that's what that little symbol means. Whereas fire service TICs, ladies and gentlemen, they pick up between 7 and 14 micron. Now, my nerd to know friends have called me out. Well, I found that ammonia, it falls into the spectral range. So that means fire service TIC's going to pick it up. You know what? That stumped me too. And I did a lot of reading on that kept me up at night because I'm like, well, why can't I see it? Here's a couple of things you should consider. Certain gases do fall within this range, but they require special spectral filtering to detect them. They're narrow band filters and they're not installed in fire service TICs. Sometimes it's coating. Whereas what fire service TICs do is they average everything in the fire service, we take an average of everything, just like pump operators. They average everything between 7 and 14 micron, which washes out signatures of gases that are in that very specific range. Now, I've had some pretty cool videos sent to me from some very smart people in the hazmat field, and they showed some type of movement through their camera. Why? Okay. Exothermic reactions that produce heat, you will pick up something if you have a background there. Ammonia, when it's a byproduct, picks up moisture in it. Moisture is a surface to the camera, and you can pick up that, but you're not necessarily detecting the gas itself. You want some interesting videos, go on YouTube and type in optical gas imaging and just watch. Instead of watching Candy Crush, watch these videos. It is crazy what they can detect. And these are not cheap cameras. I don't see them being on the fire trucks very often, but I have heard that there's a couple fire departments stepping out and really going to take their hazmat teams to the next level. I look forward to that because I think that's where we need to go. But going back to our original argument, well, it can't see gases. Why does it look like this? This is a Fire Pro 300 in Parker County, Texas. Beautiful convection currents. It looks like gases, doesn't it? Here's your answer. When hot gases rise, they bend or distort radiation passing through them. Your camera interprets it as wavy moving pattern. It's interference, like you see in heat shimmer off a hot pavement on a summer day. So your TIC's not detecting gases, but it is showing the effects of the hot gases that are having on the infrared radiation that your camera picks up. Just like you and I can't see the wind, but we can see the effects of the wind. I can see the trees moving, can't see the wind. The TIC detects the effects of hot gases across a background or surface. And by the way, a background can be the sky, just so you know. It has to have a background where it has contrast. So you can detect heat. You can't detect the actual vapor plume. That's more important. And we need to know that our hazmat friends who are way smarter than me use other things to detect concentrations, ppms, all kinds of different things that we need to be watching outside of just where it's going. So what can these movements tell us? I told you convection can tell you direction. Now, this is my video from Wilson, North Carolina. I apologize, I got them mixed up. These people are amazing people. So you can see the heat moving down the hallway in TI Basic, and you can see it going from high pressure, low pressure up the stair. In grayscale, people like myself, we get excited. We see, but a lot of firefighters don't pick that up very easily. So you can use investigative mode color palettes such as survey mode, and you can colorize this earlier by changing it to survey mode. You can push the button and hold it or double click it, and there you are. And I would caution you using survey mode in super hot environments because you will get saturation. You'll just see nothing but red, and the convection can be covered up and you won't have any discernible detail. So it's important that you understand what you're seeing and pick the right application mode, color palette, that allows your eyes, not mine, to pick it up because everyone sees colors differently. If you don't believe me, ask my wife and I what color the chair is in our house that we've had since our daughter was here. I say it's blue, she says it's green. I found out I'm wrong. I have a partial color blindness. You need to find out how your people see it because not everyone sees the same, and 5% of America is colorblind. Now, let's get to the big elephant in the room. Get this response, comment, concern numerous times a week. Man, that camera whited out on me. I know they don't white out, but what can we do? Is there something wrong with the camera? This is a picture of whiteout in a TAC probe. Just so you know, everything I'm going to show you, no matter what camera, this can occur to anyone. The phenomenon I'm going to discuss can happen to any camera based on the environment and the end user. This is when we didn't wipe the lens, the door to the container closed, some water has been flowed, and it looks like it's extinguished. It is not. Previous models of TICs prior to 2013 would produce a white screen when they overheat. And that's because many older models were single gain, high sensitivity only, and they also had a limited temperature range or dynamic range. It's also prior to the introduction of colorization, which is known as isotherms in thermography. Isotherm is just colorizing an area of interest. If you want to be specific, TI Basic is an isotherm, black, gray, white, yellow, orange, red. They pick a range in which those colors show up. Read about that in NFPA 1801 when it talks about TI Basic, and it says that shall be the starting color palette for every fire service camera with no more than 50% of the overall dynamic range being grayscale. Let me repeat that again so for my thermal imaging friends. You can't have more than half of the dynamic range in gray if you want it to be an NFPA certified camera. So newer models don't white out due to heat, but you can have issues such as moisture, gain change, uniform temperature environments. And yes, ladies and gentlemen, it's not supposed to happen, but radio frequency interference still does occur. 2013, the NFPA standard came in and they required fire service TICs to have an EMI coding, electromagnetic immunity. I'm correctly saying that right, because I'm not as techy as I need to be. Basically what that means is it prevents radio frequency interference from stopping the device from working. I've seen newer cameras not properly installed across all brands and models where the coding wasn't put in correctly. A firefighter keyed up the radio and the screen went white. This is an amazing camera showing a white screen on the picture on the left. It's not whiteout. It is simply when we're scanning from the floor to the ceiling. The problem is this camera is extremely fast. It switches between high and low gain in 3/10 of a second. But I've seen firefighters outrun that. So if you swing it around like a lightsaber and just see a white screen, is that the camera's fault or is that our fault? That's why we teach scans should be slow, because if you just slowed it down just a second, half a second even, you'd have seen that picture on the right. That's a gain change from high to low sensitivity. This is another camera doing the exact same thing. Going across a hallway, camera goes white and keeps going. 8 seconds long is this video. The firefighter missed the fire room. Let's look at it again so you can break it down. We start it, the camera pauses right here. So when we teach our scanning portion of our class, we talk about if your camera pauses or freezes, so should you. When a camera shutters, it fires a shutter or nukes. It's called non-uniformity correction. It is trying to either correct the image due to heat and energy hitting it, as they call it noise, or it is trying to do a gain change, like this is trying to switch to low sensitivity. How do I know that? The green triangle, ding, 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 pointing up in this camera indicates that. And if you know your camera, in this case, a FLIR camera has a white grainy effect just before colorization engages. Makes a beautiful picture. However, the end user has to know how the camera switches. And there are ways you can make this better too. Now, how can we fix the whiteout effect I showed you from the seek picture of the very first one? We have to wipe the lens periodically. We teach in our scanning portion that you have to stay low in the space, enter below the smoke layer. You have to call out, do a standard sweep and look around, and pick up the camera. And we need to wipe the lens. And then we're going to rotate our body 180 degrees, slow and smooth, then finish across the ceiling and communicate that information to firefighters. If at any point the camera freezes, you freeze. If it starts to fog up, like your face piece fogs up, you need to wipe the lens, the mask, and the display. I used to say, wipe your face piece, wipe the tick. Problem with that is by the time I finished wiping my face piece, wipe the tick, wipe the display, I had wiped my face piece again. Ladies and gentlemen, I'm not going to argue with you about the steps. Just make sure you do it and make sure you do it often, because the environment you're in, the camera will consistently fog up until the fire's out and all the stuff's ventilated. You're going in the worst place for ticks that could ever have been designed to be in. So you have to wipe that lens periodically. The lens has a diamond line coating on it to prevent scratching. It doesn't stop scratching. So don't use a wire brush on it. Don't scrub it with something abrasive. Clean it with soap and water, and then or a standard fire wipe before you get back to the station, and then decon it with like a very mild soap, and then use alcohol wipes on your charging contacts and the lens and the display. Do not use harsh abrasives or solvents. You will regret it. This is an example of what firefighters are calling whiteout, which is nothing more than moisture and particulate building up on the screen. Keep John Lightly's flowing some water here and what we call our thermal rebound demonstration, showing that short bursts are not effective cooling for when we're moving from remote locations towards the seat of the fire. We have to consistently flow. But during that time, after he stopped flowing, the image is graying out. The fire is not going out. We got moisture building up on the lens. Joey Baxa wipes the lens. Wow, look at that. Comes right back like turning your windshield wipers on. But if you sat here and watched this long enough, what do you think is going to happen? Is it going to stay this way? It's not a one and done. It starts to gray up again. He has to wipe the lens again. And you may view that as problematic. However, I don't have an answer, because moisture is kryptonite to thermal imaging cameras, and moisture is a byproduct of smoke. Moisture is part of the plan when we're attacking the fire. So let's talk about how moisture affects it where the tick will not work or will not work well at all. If you are in a cold smoke, high moisture content environment, such as a warehouse or commercial space with sprinkler head discharge where the fire is contained, but you have a large amount of smoke and you have low temperatures, your camera's not going to work well. The other thing would be trying to pick the camera up while they're flowing water. That's going to be very difficult, almost impossible to see. You may see, but it's going to be like if you had water gun fights as a kid and somebody got the water hose and started spraying you in the face. You can't see. You've got to be able to take a moment when he stops flowing, briefly wipe the lens and look. Placing the tick in an exhaust, bad idea. Where could this occur? People who sit at the top of the ladder and stick their face in exhaust and put the camera in it, expect it to work. Not going to work very well. Also bad news, germanium is the lens on the camera, the front of the camera. It doesn't like temperature typically above 400 degrees. As that gets hotter, it slows down the energy to your detector, which could also cause a false reading. Those of you who have done lots of searches before understand if you search above the fire while water is being applied to the fire without ventilation, it's very difficult up there, very hard to see and steamy. This is what it looks like on the third floor with an attack pro in Poland when the firefighter is 6 feet away from me after we opened the window. We'd been flowing water downstairs with an interior open staircase, and I showed them where the camera would not work well at all. Your distance, your effective range is dramatically diminished. And if you go into an environment where everything is the same temperature, the fire is pretty much out, you're remote from the fire, there are incidents where firefighters have gotten lost and disoriented because they were trying to rely on the camera in a uniform temperature environment. What does uniform mean? All the same. Your camera works by reading contrast, temperature differential. If there's not a great temperature differential and you don't have an updated newer camera with a lower thermal sensitivity, you're not going to see much of anything. And if you're like me and you have bad eyesight, good luck, because now I got stuff on my face piece. It's very hard to see. And if you think I'm being hard on cameras, you're right, because firefighters are not understanding this and they think the camera's always going to work. This is a convective flow path moving upstairs. What's happened to anybody at the top of that stairs versus these guys sitting down here below it can't really see it or feel it. If you stood on those stairs for a matter of 3 or 4 seconds, you'd feel heat. Why am I showing you this? Because this is where firefighters get injured or killed. They do not recognize a convective flow path as dangerous. DC Cherry Road, San Francisco, Mark Falkenham, Chicago, Boston. You can look them over and over again of line of duty deaths where firefighters were in a full exhaust, didn't recognize it till it was too late. And we need to honor those sacrifices, not sit here and have the same argument about, oh, I shouldn't flow water because I'm going downstairs because I'm going to steam somebody. Did you just see what was going up the stairs? Is that greater than 212 degrees Fahrenheit? Guaranteed. I can't give you an exact, but if you're worried about steam, you need to go sit in a sauna because nobody's died in a sauna yet. Okay. There are temperatures that will kill a person, and believe it or not, they're far lower than 212 degrees. And if you're not doing anything to stop heat transfer or reduce it, I've been corrected. You can't stop heat transfer. You reduce it and move it along. You're not fighting fire. Fire's attacking you. The absence of color is not the absence of heat. Use these devices correctly and understand that they don't see everything and they don't see through or far away. When you scan a room, you should never scan a room and say that room's good, we don't have to search it. I understand people teach large area searches that way. I'm not a large area search guy. I stick within the box, okay? This is a 24-foot box and we can barely see a pile of something at the end of it. At 12 feet, we can see a pile of something. For my friends overseas, that's about 3 to 4 meters, somewhere in there. I'm not exact on the measurement here. At 6 feet, 2 meters, we can tell it's something there, but only 1 meter away or 3 feet, we see 2 baby mannequins. So the farther away we are, the less effective we are, the thicker the smoke, the higher the moisture content, the difference in the resolution, the field of view of the camera, gain, change, moisture on the lens, and who is holding it. Are they standing up? Are they getting low? The majority of these problems I'm sharing with you today have to do with the position and height of the firefighter. Those who choose to walk will choose to fail. You stay high, you may die, or you'll have a very powerful, terrible, tragic story like me when I walked past a victim. I don't want you to have that story, okay? Because in these environments where there's high moisture content and everything's the same, the image can degrade, and the further away you are, you can literally disappear. You're there, but the camera has a very hard time detecting it because of what's called an atmospheric attenuation, or between you and the target is a lot of humidity. As relative humidity goes up, the energy that comes through there goes down. It's having trouble getting to you, therefore it's having trouble producing an image that's discernible or you can tell what it is. As these firefighters are close together, you can clearly see their regulator lines, their face piece, and their SCBA is dark because they're breathing. It's cool. The further away they are, it's much harder to see. Much, much farther away, they almost disappear. And background temperature. If it gets super hot and you have a lot of color, you can be overwhelmed with color. I was a color guy when I began this. I fully admit it. I was too focused on color. I'm more balanced now. I see convection and colorization is important. This is the floor in the Mile High Firefighters Conference, a great conference. Highly recommend you go to it. My guys went to it a couple times. There's a baby mannequin laying at the door, and there's another one laying inside that color you cannot see. NFPA 1801 in Chapter 6 says details within colorization shall be resolvable up to the point of saturation. In other words, when it starts getting closer to its upper maximum range, the manufacturer is not required to show you jack, nothing. Color can block out important detail. So you can have washout in low temperatures and washout in high temperatures. And then you have cameras that are dual gain that have high and low sensitivity. Low sensitivity can also equate to low detail and make the cooler areas darken down and make victims disappear. Victims can appear dark, gray, or not at all, depending on the environment, their background, the body temperature, and the camera itself. And if you want to see an example of a new camera doing radio frequency interference, here you go. Not supposed to do that. I want you to see that. I've never seen this before in my life playing with cameras. The camera went to low sensitivity due to radio frequency interference in an artificial smoke environment with no heat. That's a bad day for that device. That's an electronics problem. It's not your problem. I'm just telling you. I've tried to give you every reason why you would see a white screen, and this is the one reason that's not your fault. This is a manufacturer issue. It's happened across every brand I've ever touched. So know that the same people who put together cameras work at multiple different places, and they have bad days just like you and I do. And sometimes things don't get put together. Send it back, get it fixed. But if you're not checking your radio, checking your tick out in the morning and keying up a radio, you will not know this until you go in a fire. So when you check the tick in the morning, it shouldn't be on, off, battery's full, swap the battery. It should be on, you should check it, look around at some objects, let it go through a full flat field correction, which takes 30 seconds. When it stops clicking, look at a few items, do some scans, then get your radio out, do your radio test close to it. Go look at the stove, go look at something. Get you 5 minutes in with the camera. If you know it works then, you got a better chance of working later. Ladies and gentlemen, I always conclude with trying to give you more resources. Every webinar we do, I give you a copy of the presentation, a link to where the webinars are stored, and access to our YouTube channel. I want to thank you for using that as our YouTube channel has grown. We have now 26,000 subscribers. We'd like to see that increase. The only way that's going to do so is we continue to post content, you continue to use it. The Google Drive has all kind of resources, not just Seek, it has FLIR, Bullard, all kind of stuff. But if you go under the Seek public shared folder, you will find a copy of this presentation and every presentation I've done for the last 2 years, free for you to use. We just ask that you cite Insight Fire Training. You want to see this webinar, give us a couple days, we'll get it uploaded onto YouTube and on our website. And if you want to use our YouTube resources, go to YouTube, look across the little search bar, and you'll see videos, playlists, all kind of different things. Hit playlist. Our stuff is organized by brand and subject matter, like size up, all that's listed there. Check it out, like, share, subscribe. We greatly appreciate it. And we thank you for your time today. This is my contact information. If you have any questions, you can email me either through the website or through that email. If you go to my website and hit contact us, it goes straight to me or one of my guys. We greatly appreciate it. God bless you. Gordon, I'll hand it back over to you.
Awesome, thank you. And like Andy said, if you guys have any further questions after this webinar, just please feel free to reach out directly to Andy or myself, and we'd be happy to answer those questions for you guys. If there was something Andy mentioned that you wanted to go back and reference, we will be sending out a recording of this webinar to everyone who registered today, most likely today. So thank you, Andy, for your time, and thanks to everyone for registering for today's webinar.
Thank you.
Thanks.
Take care.